And here we are. Hello again, everyone.
Yeah, once again. All right, hi, I'm Romain from the Android Toolkit team.
And I'm Chet Haase from the Developer Relations team.
So today we want to give you a presentation about graphics on Android. We thought about this because over the years, Chet and I, we come from a background doing graphics. We often help developers with graphics questions, and we realize that many app developers have to deal with graphics at some point, but it is not your expertise. This is not what you do all day long, and that's completely fine. But what we found out is that graphics is a very large field, and some fundamentals can be extremely helpful to understand and use graphics APIs in the best way possible. So initially, we wanted this talk to be a grand tour of the world of graphics, what are all like 2D graphics and 3D graphics and ray tracing and sign distance fields and all those things. And then Chet started working on the slides, and we realized that this talk should be at least 10 hours long. So think of this as the part 0 of probably a series of talks that we're going to give on the world of graphics. So most of what we're going to say is not specific to Android. So today we're going to focus on 2D graphics, and mostly 2D graphics, because it's going to be just a very bare minimum you need to know. So with that, let's get started. And we're going to start with the most fundamental brick of graphics, of 2D graphics, obviously, and it's the pixel. So Chet, what is a pixel?
So yeah, we're going to build up from the very bottom. And you may be thinking, why do I care about pixels? And that's what we're here for, is to make you care about this stuff, because it is interesting. So let's pretend that you are seeing the screen of a white monitor, and you probably don't have to pretend very hard, because that's probably what you're seeing right now, is this white image on your monitor. And that's what it looks like to you. But if you looked a little bit closer, if we zoomed in on that, that is not one solid color, but is rather a grid of things that we call pixels, or picture elements. And in fact, if we zoomed in even further, you see something quite different at the lowest layers of the hardware. Let's pretend that each one of these is one of those picture elements, one of those pixels. And what we see is not actually this white square, but rather some sort of representation of RGB information. So we're actually seeing not white, but we're seeing red, green, and blue information being blasted out, which mixed together over the entire screen give us that impression of white that we get when we're actually looking at it. So the question is, how does this work? And it's through something called additive color mixing, where basically you have the color information from those RGB subpixel elements, and you add in distance, the distance between those pixels and the viewer, or you or me, and what you get is the mixed color as a result. So when we're looking on the previous slide, when we're seeing all those pixels up close and the RGB information, it's as if we have our eyes sort of plastered at the monitor, and then we're seeing these really tiny things, but we're seeing them up close, so we see them separated. But it's a little bit more difficult to see pixels like this, where that teeny tiny bit of hardware is far away from the viewer, and then it mixes over the air, over the distance, to actually get this additive mixed color of white. So then you can think of that, the red subpixel element is sort of broadcasting this cone of red color information, then blue and green, and those are mixing together in a way that's really hard to approximate in Keynote. So I'm going to take a different representation and say, what if we were looking down on it? I'm going to have a black background here because it's a little bit easier to see what's going on. So the red is going to mix with the green information, and those mix to give us yellow. And then when you add in blue on top of that, that mixes with the other colors to give us white. If those are all in full extreme power, they're going to be broadcasting, full on red, green, and blue, and we're going to see the impression of white on our end. So at this point, I want to take a little interlude into art history. So I spent a bunch of time thinking about colors and images and computer graphics in grad school many years ago. And as part of this, I looked into some amount of art history, specifically pointillism. So there was a famous artist in France called Georges Seurat. And I believe he certainly perfected the art of what is called pointillism. And instead of the traditional mechanism of mixing colors that were applied to a canvas, so the artist would mix, whatever the colors needed to be to come up with the colors that they wanted on the canvas, and then they would apply the color directly to the canvas. Instead, Seurat and other pointillist artists would apply more like primary colors on the canvas, and they would do it in little dots, and then they would depend on exactly the additive mixing that I was talking about with RGB to mix the colors correctly to give the viewer the impression of what was going on there. So what we're seeing is the overall image here on a Sunday on Lagrange shots is not what you see when you actually zoom up on the canvas, because it is using this really bizarre, incredibly engineering approach to painting where they're just dots on the canvas. And what you get is a much brighter value of those colors because it is avoiding some of the subtracted mixing of traditional oil painting that we'll talk about in a little bit. So I don't, unfortunately, have a high enough res picture from the Chicago Art Institute where I took this to zoom in here, but I did take one of another one. This one's by Paul Signac. This is called Evening Calm. And if we take a look at this area here and we zoom in on it, you can see the pointillist approach where it's just dots of colors, which when you step back from it, give an overall impression of the color and a much brighter impression of that color because it is using the additive approach to be able to retain much more of the brightness of the light in the room for your eye to pick up. All right, so we have these two essential ways of mixing color. There's the additive we've been talking about and subtractive. Additive basically adds in color information, right? You can think of this as being colored lights, which is essentially exactly what is going on with pixels. You have a red light, a green light, and a blue light, and they are combining and adding to each other to get a mixture of light and color information for the final color that we perceive in our eye. Also, to some extent, watercolors are additive because there's not such a thick layer to sort of filter out a bunch of the colors going on, but you basically have a white canvas that is then blowing through this this information, this colored information through watercolors. It's kind of a combination of things, but it's certainly not as subtractive as oil paint mixing. And bright paint colors, like in the pointillist example, basically mostly reflect the light there. That's why we're able to get a brighter impression from pointillism than from more traditional means of mixing colors. So we can see a visual of this over on the right. If we have red, we mix it with green, we get yellow. We mix in blue there and we get white. And we also get these secondaries of this yellow, magenta, and cyan, depending on the proportions that we mix them in and how bright the primaries were to begin with. Subtractive mixing, on the other hand, as the name might imply, actually subtracts color information. So mixed oil paints is one of those, and we'll see a bit more information on why that is. Romain's going to talk about how the substrate of oil paints work. And colored light filters do this. So if you imagine if there's a really bright white light shining at you, and then we put a red filter in front of it, it's going to subtract information out. So what we're going to get is a colored version of that white light by taking away some of the other colors that were in the scene to begin with. So here, there's different primaries for subtractive. It's basically the secondaries for additive. So we have magenta. When we mix that with yellow, we get red. And when we mix it with cyan, the overall color is black, although as anybody knows, when you mix paint colors together, what you really get is brown. No matter what you're mixing and how much proportions, you just get brown. That's my experience with oil painting, at least.
All right, so Chet just talked about paints and mixing paints. So here's what happens at the physical level with light. So you have light coming in, hitting the surface, the paint layer on your canvas. Part of the light will be reflected directly, so that will depend on the type of paint. But some paints are more glossy. You're going to see reflections of light around. So that's the part of the light that's directly reflected. Some of the light will penetrate the paint layer and will get scattered and absorbed within that paint layer. But some of the light eventually will come back out, and what will come out is the result of that absorption phenomenon. So when you have, let's say, a red paint, it's exactly what Chet described with a red filter. It's just a paint that absorbed everything that was not the red part of the light spectrum. And if you look at the diagram, the outcome of this, that you're effectively end up with the concept of additive lighting that we find in our displays. Just like we went through an extra step before, we had to subtract light before we can send back towards the viewer. The outcome of that is when we look at paintings, so this is an example of a painting that I don't know why, like always made me uncomfortable. It sits in Chet's living room. And you can see that in that painting, only the white parts are actually close to the kind of brightness that you can get from a display. But even then, like it's never going to be as bright as a display because you need light to penetrate the paint layer. Some of it will always be absorbed no matter what. It will be reflected off of the white canvas. The white canvas itself is not going to be perfect. So you're never going to have a perfect white. But aside from that, all the other colors are much darker, much richer than the kind of stuff that you get from a typical display. And if we look at actual displays, this is how they work. So earlier, Chet mentioned that every pixel is made of just little tiny lights, and that is exactly the case. So this is a macro photo that I took of my 4K TV that sits in my living room. And if you zoom in close enough, you can see every individual pixel. You can even see the electronics between each pixel. So each pixel here is made. So there was a picture displayed on screen. I think it was close to white. You can see there's a red component, there's a blue component, there's a green component. And interestingly enough, this particular TV, this OLED TV, also has what seems to be a white component. So this is a trick, we talk about RGB, but some displays use extra white lights, for instance, to increase brightness, or at least the perceived brightness. But even if you set that aside, you can see that the blue component is bigger in surface area than the red and the green, and that's because our eyes are not as good at perceiving blue. So we need to emit more blue from a display to be able to perceive it at the right intensity. Now, if we look at a Pixel 4 device, again, I took this macro photo of my Pixel 4 when it was displaying pure white. And as you can see that this white at a fundamental level is just made of red, green, and blue. Again, you can see that the blue is a larger pixel. There's twice as many green components because our eyes are more sensitive to green, so it's very important for perceived brightness. So instead of having a white component per pixel here, we have more green because it will help our eyes perceive the brightness. So yeah, and the fact that we sit far away from the phone or from the TV is where the magic happens, right? Like all that colored information gets mixed when it reaches our eyes, and then the brain does its own magic. We could do a whole presentation on just how the eyes work. It's fascinating, but we're not going to get into that right now. All right, so why do we care? We care about RGB mostly because it's a very common way of describing colors when it comes to graphics and graphics programming. And of course, you've used RGB values in your applications. A great example is that you want to paint a background in your custom view. You're going to use canvas to draw color. Here we said 255, 0, 255. And those magic values mean that we want to mix red and blue, and we're going to get magenta. Also, frankly, this is very interesting, and Chet and I are big believers in trying to understand the fundamentals of a domain to be able to be better programmers in that domain. Now, if we look at those magic values, 255, 0, 255, we said, okay, we mixed red and blue, and we end up with magenta. If you take a step back, you might want to ask yourself the question of, okay, we have those values, but what is a color exactly? Like, is there a red? Is there a blue? So we need to dig a little deeper. So a way to define a color is in this manner. A color, as far as software is concerned, it's a tuple of numbers. It's often a triplet, like in RGB. And these numbers live in a color model, and they're associated with the color space. So we're going to take those things one by one. So first, a color model. The color model effectively defines the number of values you're going to have in the tuple. So RGB, again, you have a triplet. It's a pretty well-known color model, very common. There are other color models like LAB or LAB. There's YUV, there's HSL, HSV, many of them. And then there are some color models that have more values. So for instance, CMYK, right? Like CMYK is designed for printing because those are the subtractive color primaries. And there you need 4 values to be able to describe all the colors. But we're going to focus on RGB as our color model. So, we take RGB and we have our triplet of numbers. Those numbers can be represented in different fashions. So they're just about storage. So you can use a hexadecimal value. You can use decimal values between 0 and 255 that fit nicely in a byte. or you can use floating point values. But that almost doesn't matter. Like, still, the question that's interesting to us is like that 255 for red or that 1.0, is it one specific color? Like, are we talking about one red? Is there an absolute red that we can define this way? The answer, I mean, you might have guessed because I asked the question, is no. So if we look at the spectrum of colors that we can perceive in our eyes, and there are different ways of representing it, but this is a common one. It's called the chromaticity diagram. So those are all the colors that we can see with our eyes, right? So like, our eyes are effectively radio receptors, and a very tiny part of the radio wave spectrum is the visible light spectrum, and this is the part of the spectrum we can see. The diagram is actually more complicated. It should be a 3D diagram. Our eyes are better at seeing in the darks, and we don't perceive views in the lights as easily, but suffice it to say that we can use that as a base. So anything that falls in that diagram we can see. Anything outside is called imaginary colors. It's radio waves that we are not equipped to perceive. Now, if we go to the next slide, and we use 3 additive lights, or red, green, and blue, in the color model of RGB, we can only create a triangle, right? We can only represent a portion of the visible spectrum. We could theoretically create a triangle that contains the entire spectrum, but it would also contain a bunch of colors that we can't perceive, which would make it very difficult to use properly. So that's what a color space is. A color space is just a slice of the visible spectrum, and that will help us define what colors actually are. So if we go to the next slide, there are different color spaces that exist. The most common one is called sRGB. If you look at the diagram on the left, it's that blue triangle. Then we have Adobe RGB. It's also pretty common. That's the orange triangle. And Profoto RGB is just another example of a color space. Now, if you take a look at sRGB and Adobe RGB, if we look at, for instance, the color 0 to 550, so pure green, that pure green will be at the vertex that's at the top of each of those triangles. So the pure green in sRGB is not the same as the pure green in Adobe RGB. So this is a fundamental thing to understand about color. When we use those numbers, we can't use those numbers without a context. They need to be defined in a color model and in a color space. All right, so that's enough theory. Where are pixels actually used? Ideally in your application, nowhere. They're technically used everywhere, but you don't want to use them directly, right? They are the fundamental building blocks of graphics. They're kind of like our atoms. You can address pixels individually on canvas. For instance, you can draw a point and you can draw a single pixel, or on bitmap, you can set or get every pixel individually. But usually, unless you have a very good reason to do so, you should not do that. There are more efficient ways of doing this. There are exceptions when you're a graphics programmer. For instance, when you write code for the GPU, you use something called fragment shaders. There are programs that are executed by the GPU for every individual pixel on screen, but that's not a problem that hopefully you will face in your application. Instead, you want to use higher level primitives. And the first one we're going to talk about is bitmaps. So bitmaps are also called images or pictures, although we're careful because there is a class called picture on Android, and it's actually not a bitmap, it's something else. It's related to vector graphics. And bitmaps are important because a lot, if not most, of the content that you see on your computer, on your phone, is actually made of bitmaps. Things have changed a little bit over the years. We use more vectors, and we're going to talk vectors in a bit. But every photo that you see on screen is obviously a bitmap. A lot of UI elements on Android, they used to be made of bitmaps. Now we use more vector drawables, but still very common in UIs, like all the icons and so on, to be made of bitmaps. And surprisingly, and Chet will explain you why, text is also made of bitmaps. Yeah, go ahead. Sorry, I was about to keep going. It's your turn.
So one of the things that's apparent about bitmaps, once you scratch the surface, is what's with all the format files, right? So we have JPEG, we have GIF, we have WebP, PNG, TIFF, BMP, like all these different ways of storing the information. But we just saw the representation of pixels. It's really simple, right? It's RGB information, at least for computer graphics stuff. So what's so hard about storing that? Why do we need so many different ways? Why are there all these different file formats? And it turns out to be trade-offs between size and capabilities of all of these. Like, we'll see some examples of this where if all we want to do is store the RGB, we're going to end up spending a lot of space, a lot of memory to do that. So there are more efficient ways to do that, and the file formats are basically trade-offs in the algorithms that they have to compress and make these things smaller. So let's look at some examples. So let's say that I had this tiny little image. It is all white and it's 100 wide and 100 pixels high. And if we store this in BMP format, it turns out to be 40K, which not coincidentally is 100 times 100 times 4. So what's going on is BMP is exactly the trivial way of storing color information or bitmap information that we thought file formats might be doing already, which is it just has the RGB information for every pixel and it stores all of those pixels. So the file size of any BMP image is width times height times size of an integer, which is 4 bytes. Now it's only storing 24 bits of information because it only needs R, G, and B, and it doesn't have anything for that fourth, but it's easier to pad it out to an integer and store it as integers because addressing sub-integers, especially in the time period where this file format was created, kind of a hassle, so I might as well pad it out to an integer. If instead we store that as a JPEG, JPEG has different levels of lossiness, but at least in the example I used here, turns out to be 4K. So there's a 10x saving just by using the JPEG format to store this simple file that we have, this simple white image. If we go to GIF, bigger savings indeed, 156 bytes for this thing. So it's doing something very interesting. It's knowledgeable about what's going on in there. Hey, there's only a single color. We could probably store this in a much more efficient way. PNG turns out a little bit better than JPEG, not as big as GIF for this particular example. Let's take a look at a different example. So we have this diagonal gradient where it's storing a lot more color information, but it's not really lined up on scan lines, which may be advantageous for some file formats. BMP, again, 40K. It's storing exactly the same kind of information. It doesn't care what the colors are. It's just going to store them as individual pixels. JPEG, a little bit larger at 6K. GIF, a lot larger than it was before at 3K, and PNG larger still. Now let's look at a more interesting example. So here's a landscape photo, much bigger to begin with. So 6,000 by 4,000 BMP, 96 megabytes to store this thing. JPEG, only about 5 megabytes. GIF about twice that. So all of a sudden JPEG is looking better than GIF for this particular use case. And then PNG, lossless format at 24 megs. But here's where it gets interesting. So we've been talking specifically about the file sizes. So why is that? Well, let's take a look at a comparison between JPEG and GIF. So JPEG over on the left looks fairly close to the original sort of raw photo that I took. But now if we look at GIF, I don't know what it shows up like on your screens. I can't control that. But if you look up in the upper right quadrant there, you can see that there should be a really smooth gradient as the sky goes from bright blue to a much darker blue. And what I see in GIF is banding. It basically has these waves of color information, or at least that's what it comes across as. And the problem that it's dealing with is it only has 256 colors. It's not always the same 256 colors, but it is limited to 256 colors they can have across the entire image. So there's simply not enough information in there for it to represent that really smooth blue gradient in addition to everything else going on in the image. And that is one of the trade-offs. Maybe sometimes it's smaller than the equivalent in JPEG or PNG, but maybe it doesn't have enough color information to really give the quality that you want in that image. If that one didn't come across well, then here's another example. Maybe it's a little bit clearer. Here's the diagonal gradient, and you can see the banding in the GIF image on the right. If we zoom into the upper left quadrant here, you can see the banding even more extremely. And again, it's because it just doesn't have enough color representation, color information to represent all of the colors that it needs to across this wide spectrum. So some of the differences, actually, Romain was going to talk about this one.
Yeah, so there are obviously differences between those formats, right? Like, so JPEG uses what's called a lossy compression. So to save this space on disk, you're gonna hurt the visual fidelity of the image. And the nice thing about JPEG is that you can choose how much you want to sacrifice in terms of quality to save space on disk. JPEG also has the drawback that it's opaque only, so you can add transparency by having a sidecar file, but that's not great. GIF only has 1-bit transparency, so a pixel is visible or invisible, but you can't do any form of anti-aliasing on translucent edges. Like Chet mentioned, you only have 256 colors. You can actually use more. There are some tricks, but we're not going to get into the details. Suffice it to say that GIF is not great when you need more colors. PNG uses instead lossless compression. So it's going to retain all the visual information, but of course the files are going to be bigger, but you also gain the translucency. You have an alpha channel over 8 bits, so you can have those nice smooth alpha transitions. WebP is a more modern format. So WebP is interesting because it can do a lot of things. So WebP can be lossy. It can also be lossless. So you get more control over what you want. It's kind of like the JPEG and PNG combined together, and it does support an alpha channel. In addition, WebP, just like GIF, offers support for animated images. It shouldn't quite replace videos if you have like super high resolution, although maybe WebP, but for GIF, definitely like don't store high resolution videos in a GIF because they're going to look bad and they're going to be huge on disk. It's actually funny. I think some of the websites like Twitter or other websites, when you upload an animated GIF, they turn them into MP4 because it's more efficient that way. And finally, BMP is just the raw data. So BMP is actually useful as an intermediate storage format if you want to keep all the information. But there's very little reason to use that in production. And even as an intermediate storage, there are better solutions out there like PNG because it's lossless anyway. So the takeaways. Make sure you use the right file format for your content. So any high frequency data like a photograph will benefit from using JPEG, for instance, or lossy WebP. You're going to save a lot of space, and the user won't be able to see the loss in visual fidelity. The amount of color, the number of colors you need. For instance, if you're going to compress an image that contains only 2 colors, a GIF file might be super efficient. A JPEG is not going to be as efficient. If you need translucency, you're going to use WebP or PNG. Size may be more important to you, animations may be more important. So for every file, just make sure like you think about those different formats and you pick the one that fits the needs. What's more important about file size is that it is not correlated to the size of that bitmap in RAM. And it's a confusion that we've dealt with many, many times over the years, and even very recently. I remember helping a team at Google that was using a 3D engine, and they were complaining about the amount of RAM that was used after loading a model. And I looked, and they're like, and so I asked them about the size of the textures. They're like, oh no, that's good. Like the textures are only 4 kilobytes. And I looked at the textures. They were 4 kilobytes on disk because they were PNGs, but they were 4,000 by 4,000 gray images stored as PNGs. So they compress really well, but every one of those textures was taking many, many megabytes in RAM, and they had a bunch of them. So they didn't realize that their tiny asset on disk expanded to be huge in memory. So yes, with a very small JPEG, you can run in and out of memory error. So let's take a look at an example. So we have this 100 by 100 image that Chet showed earlier, just a white square. It's 4 kilobytes on disk as a JPEG. And if we decode it as a bitmap, and then we print its dimensions and the number of bytes that it uses, we're going to see it's 100 by 100, and it uses 40,000 bytes. So it's a 40 kilobyte image, so same as the equivalent in BMP. That means we have a 10:1 compression ratio with JPEG on that particular image. Just loading it, it's going to take 10 times more memory. Now, if we take a bigger version of that image, still white, 2000 by 2000, it's 67K on disk. And if we load it, we're going to see that the image in memory takes 16 megabytes. That's a 238 to 1 compression ratio. So again, do not trust the size of a file on disk to get an idea of how big it's going to be in memory. It's always going to be, at best, the same size, but probably most of the time bigger. That also means that if you want to have a rough idea of how much an image is going to use in RAM, you can do the math, or you can just save it as an uncompressed BMP and look at the size on disk. Uncompressed BMP is going to be raw data. So what should you do? Nobody wants to hear that. Java and Kotlin programmers manage the memory. Only load the size you need. That's particularly important, especially if you put bitmaps in your drawable folders. Remember that the base drawable folder, without any qualifier, is actually the MDPI folder. So any image that you put in there, when loaded on a modern device, will be upscaled by 4x on each axis, which means it's going to be 16 times bigger in memory. It might actually be too big to load. So use the right DPI folder, or you can also use the drawable-no DPI to guarantee that it's not going to be rescaled on any device. So only keep the bitmaps you need around, use a good bitmap cache, reuse bitmap memory. We've given talks and we have articles about that. Or better, because doing all those things is difficult. It's difficult to do it right. Use a library to do this for you. There are several libraries available, Glide, Picasso, Coil, and others. So if you're interested in Coil, for instance, we recently interviewed Colin White on the ADB podcast, where he explained how Coil works. So then on Android, how we draw bitmaps, there are different ways. You can draw them directly on Canvas using canvas.draw bitmap, or you can do it indirectly, right? You can wrap bitmaps into a drawable, or you can load them into an image view. And actually on Android, it's often more convenient to do it indirectly by going through drawables and image view.
So earlier we talked about text being drawn as bitmaps, which is maybe counterintuitive because aren't font glyphs actually represented as complex curves? In fact, they are. So these sort of Bezier curves that represent each of the characters that we use in text. And they are drawn with complex paths, typically into bitmaps. And why? Because it is faster. So if you think about it, if every time we needed to draw this complicated, Y glyph, we had to, essentially figure out how to draw a path. Well, that would be a lot of operations, and text is really, really common. You have all these characters appearing all the time on the screen, and you don't want to slow down your fling of that recycler view just so that you can draw really complex paths for every character. So instead, let's do it once, and then let's copy bitmaps around. Copying bitmaps tends to be a really fast operation for CPUs, but it's even faster for GPUs. They're really good at basically copying around textures. And so that ends up being how it happens at a lowest level. So let me show you an example. So let's say we want to draw the string cool onto the screen. So the 4 characters, COOL. So we start out with the information in the font, this representation of each of those glyphs, probably some Bezier curves. So we've got curve representation for the C. Then we're going to go through the free type renderer, which is a renderer used by Skia, the lowest level graphics engine that we have in Android since before 1.0. And then we're going to draw to something that we call the glyph cache, which is basically a bitmap or a set of bitmaps that we have pre-allocated in memory for exactly this purpose. And we're going to do the complex path rendering into that bitmap, and there it sits. Then we go on to the next character. We're going to, again, use the free type renderer. We're going to draw that into the glyph cache, go into the next character, and we're going to start to draw that and realize, no, we already have an O. There's no reason to have more than one character. So the glyph cache holds each of the characters that's been drawn at any of the sizes that it has been drawn. And then it doesn't need to repeat that. It can just copy from that same single instance that it has. So then finally, we draw the L into the glyph cache, and then we're ready to actually draw the string onto the screen. We do that by essentially executing a draw bitmap somewhere in the system, and then it appears character by character on the screen or in the buffer. And there we go. Very fast and efficient. That first time, not as much, but we only had to do it once. So another thing to be aware of in bitmaps is scaling and the artifacts that can result, and then making sure that you're doing the right things with the right kind of attributes and the right kind of source images to begin with, and be aware of the artifacts that can result. So one of the artifacts comes from upscaling from a bitmap that just doesn't have enough information. Let's say you load in an image and you load it as a thumbnail, and then later you want to draw it at the full size of the screen. Well, it's probably going to look pretty awful because that thumbnail didn't have enough information. And once you upscale it, you're going to see the lack of information, and the user is probably not going to appreciate it. Downscaling can also create artifacts depending on the kind of filtering that you're doing. Now, when you're downscaling, you're sizing from a higher resolution image down to a lower one, and you do have the information that you need, but if you're not sampling that source information, the original bitmap, and filtering appropriately, then you can also get some artifacts from that downscaling operation. And finally, when we are using bitmaps to represent some sort of geometry, which is typical, especially historically, for the UI widgets, let's say the background to the button, well, those things need to scale on the screen to be different sizes of those UI widgets, and scaling geometry represented as bitmaps can get weird. And so we're going to see some examples here of how that happens. So let's say we have, this is a really huge version of it, but let's say it's just a 4x4 pixel grid with these RGB and black RBG and black stripes here. And let's say we want to downscale that to just a 2x2. If we use a point sampled approach, it's just the simplest one. It basically says for every pixel in the destination, go find the nearest pixel in the source and pick that color. It doesn't think about it at all. It just pastes it in there. And then we end up with just a subset of the information that we had in the original image. Instead, a typical and pretty easy filter, and I believe it's the default one we do downscaling in Android, is bilinear filtering, where we look at not just the destination pixel, but also the pixels that surround it. And then we combine that information into the final result. It obviously doesn't look like the original image, but if you step back and squint, it's a lot closer in color approximation than the one in the middle, because at least we're combining all of the color information from the original image into what we've got in the smaller image as a final result. There are artifacts, as I said, that can result from upscaling as well. So let's say I want to draw a line. This is this vector line that I drew in this really tiny bitmap. And that's represented up there in the upper left. And then as we scale that up, we can see the artifacts more and more clearly, where the one over on the right, it doesn't look like a line, it just looks like a series of boxes, because that's essentially all that it is, right? The size at which I drew that line, it's just a handful of pixels. So if we scale it up too large, then we just don't have a lot of information to work with there. And so you get this kind of crummy result in the end. Now, there are ways of filtering this so that you could smooth that out a little bit. So now if you squint, it looks a little bit more like a line. Still not great, but filtering can help basically as a workaround for insufficient information. Downscaling can also get weird. Let's say that I draw a large image and it has this checkerboard pattern in it, and then I want to downscale from there. So if I do it with point sampled filtering, we get some really weird random results in there, because we're just randomly picking the pixels that we take the color from in the source information, and then we get these varied patterns as we go down and down the scales. If instead we use bilinear filtering, then we get a little better approximation of the original color information. There's still some artifacts depending on how much we're downscaling, but filtering does help as a general workaround anyway. But here's where it gets really weird. It's in UI geometry. So typically, until we started using vector drawables for a lot of the UI widgets, we were using bitmaps, right? And we would use it, let's say, for the background of a button. So let's pretend that the simple graphic that I have there, the rounded rectangle, is going to be the background for a button. Now, you can imagine if we have a small word in English, and then the application automatically, localizes it to German, it's going to be much longer. I can guarantee it. German has really long words. And it's going to need to scale the background, right? And we don't want to produce separate bitmaps for every possible size of that UI widget. So instead, we want to scale it automatically. So if we do that, if it's just a bitmap and we scale it to arbitrary sizes, let's say we make it wider and wider, then we end up with these weird artifacts where, because it wasn't geometry, because it was a bitmap, that's not a rounded rectangle anymore. That's more like an oval, because we just kind of stretched the corners too much. And that's essentially why the team came up with this thing that we call 9-patch, which gives us the ability to scale the parts of the bitmap that can scale correctly, but to copy the parts of the bitmap that really shouldn't be scaled because of the artifact that we're talking about here. So if you use the 9-patch tool in Android Studio, it looks like this, and you define the areas that are scaled versus copied. So the scaled, represented by the magenta in the middle, that's going to scale correctly as we go along, sort of vertically and horizontally, but the corners of the buttons are the ones that we want to copy instead, giving us a result like that, where even the one that's really scaled quite long at the end comes out looking like the round rectangle that we wanted. And I should point out too, it's not actually 9-patch, because you can represent even more than 9 quadrants. It's more of an N-patch.
All right, but 9 patches are just a workaround, and what's better than a workaround is a fix. So what you really want is a geometry. So geometry is also called vectors. Vector graphics are effectively canvas commands, they're drawing commands. So the common ones are draw line, draw path, and with those two things, you can represent anything you want. And you can think of those as the mathematical representation of the shapes. And through a process called rasterization, we can transform this mathematical representation into actual pixels. So an example of vector format is vector drawable. If you peek inside, you will see a lot of XML. So you're going to see, rotations, and you're going to see path tags, different attributes. And what we do at runtime is that we load all that information and we just interpret it as a bunch of canvas commands. So in that example that you see on screen, we have a path with a fill color and a pivot. And when we look at what happens on canvas, for the pivot and the rotation, we set a matrix. For the fill color, we're going to set a fill style for the path. We're going to draw a path with that style. And the path data tells us how can we build the path object with the move in lines and curves. So now this is just one example of format. There are other formats like SVG or Lottie. Lottie is exported from After Effects, also interpreted at runtime, also translated to canvas command, much richer than vector drawable. And it kind of requires a tool like After Effects to be able to produce those files. But you can do like really, really complex animations that will work at any resolution. So I mentioned the concept of rasterization. So what is rasterization? So let's say we start from a simple path. So this path is made of a single curve. It's called a cubic curve. So when you draw a curve like this in a design tool, next slide, Chet, you will see two handles, right? By moving those two handles, you can change the shape of the curve. And those two handles are very important in the rasterization process. So I'm just, the process I'm gonna explain is one way of doing it in software, like it's very different on GPUs, but it gives you a good idea of what happens behind the scene. So we're gonna take the midpoint on each of those handles. Then we're going to draw a line between the end of both handles. We're going to find the midpoint there, and we get those new pink lines. On each of those pink lines, we're going to find the midpoints again, right? It's a recursive process that gives us a new line, the green line. And there we're going to find the midpoint one last time. That last point will be on the original curve. And incidentally, it's also a point where we can split the original curve into two subcurves. And if you look at all those lines that we've drawn, like the green line and the pink line and the original blue line, you can see that we found the new handles for those two new curves that are part of our path. So we started with a curve. We found a point that lets us split the curve into two curves with the new control handles. And then we can repeat this process over and over again until we have done it enough. So the question is, what is enough? When do we stop? So there we look at something called the flatness of a path. So we draw a line between the start point and the end point of a curve, and we look at the height between that line and the highest point on the curve. When that height is deemed small enough, in the case of rasterization, it's often going to be like, let's say, less than half a pixel, then we know the curve is very, very flat, and a very flat curve is a line. So when we found a curve flat enough, we can approximate it and replace it with a line. So what we're going to do is we're going to subdivide our curves over and over again until we're left with just straight lines. And then we can render those straight lines very efficiently and very easily. And you have a result like we see on screen. You can see the pixels. And we can do this at different resolutions. On the next slide, you can see the same curve rendered at a different resolution. We just have to change our flatness to adapt. So that's a very simple algorithm, and it works extremely well. We also have an API on Android called flatten or approximate. Here's an example using the KTX extension. You can call path.flatten, and you can specify the flatness that you want. By default, it's less than half a pixel. It will give you all the straight lines that make the path. So if you want to walk the path for an animation, you can use that to easily deal with it because it's just going to be a bunch of straight lines. So once we have all those straight lines for a path and we need to fill the path, so here I have an example of a star inside a circle. We want to create a cutout. How do we do that? Turns out it's just a problem of filling a polygon, and that's a pretty easy thing to do. So there are two different techniques. The first one is a fill rule that's called even odd, and you may have seen that name in different tools or in our APIs. So the way it works is we start outside the path. We take one of the scanline, a row of pixels. We initialize a counter at 0, and then we start walking to the right. And when we found an intersection with the path, we increment our counter. And when the counter is odd, we are inside the path, and then we start filling the path with whatever color you said you wanted. We find the next intersection, we increment the counter, now it's 2, and now the counter is even. So when it's even, we are outside the path, and we start filling it, so we just skip the pixels. Another intersection, we increment, 3, odd, we're inside the path, we keep filling. So now we filled one row of pixels. If you repeat this process for every row of pixel that makes the path, you end up with the result that we expect. There's another rule, it's called the non-zero, and this one takes into account the winding of a path. So the winding is just the order in which the points that make up the path are defined. So the starting point of our circle and our star here are the red points, and the second point is to the right, we're going to have a clockwise winding order. And it's going to be very important, and you'll see why in a second. So to fill a non-zero path, we start outside, we have our counter set to 0, we find the first intersection, and at this intersection, we check whether the line that we approximated from the curve goes up or down, and the way and whether it goes up or down is based on the winding order, whether it's clockwise or counterclockwise. In this example, the line is going up, so we increment by 1 our counter. It's 1, it's non-zero, so we're inside the path and we start filling it. Another intersection goes up, we increment, now it's 2, we keep filling because it's non-zero. Another intersection, it's going down, so we're going to decrement the counter, but it's 1, it's still non-zero, so we're still inside the path. And then we do that for every line, and we end up with a completely full circle, which is probably not what you wanted. The way to fix it with the non-zero rule is to simply change the winding order. So we can keep the same winding order for the circle, we can change the order in which we define the points for the star, and then I'll leave that as an exercise for the reader or for the listener. And if you re-execute the algorithm, we're going to end up with this result. All right, the last thing I wanted to talk about when it comes to path, I wanted to also demystify the concept of stroking a path. So here we have a path, it's a simple circle, but we want to stroke it so that we end up with a donut instead. So the way it works is that you take the original curve and you offset it so that you have 2 new curves, one inside and one outside. And those 2 new curves, as you can see, they form a new boundary. And if we fill those 2 new curves, we end up with the stroke. So stroking is very interesting because all we're doing is that we're extruding the original path. And then we can simplify the problem by saying, wait a minute, that is a closed path, so I can just fill it. So a stroke is just a path that was generated for you, and that was just filled on your behalf. Typical trick in graphics programming, you try to reuse stuff as much as possible. And paths, for instance, are very important because when you draw a rounded rectangle or even a circle for that matter, what happens or often happens under the hood is that those things are just recreated as paths. So a circle can be approximated using 8 curves, and will look close enough to a circle when we rasterize with pixels. And same thing with a rectangle with rounded corners or straight corners. Anyway, so that's all the time we have for today. There are many, many other things that we'd love to talk to you about, like GPU support, how does it work, anti-aliasing, gradients, clipping, blending. The world of 3D is a whole other set of presentations. So thanks for your time. And yeah, we'd love to do follow-ups to this presentation to explain everything else there is left to explain.
Yeah, hopefully this is not like History of the World Part 1, where they never intended to actually have a Part 2. We would love to do more on this. We just realized it's going to take more than one presentation. Also, thanks for your questions. I've been looking at them as they came in. Unfortunately, we're already 7 minutes over, and I think the next session begins in 2.5 minutes. And so we should probably leave it there.
If we, I mean, we can answer them really quickly, right? I'll go in order. Runtime hit when using vector drawables in comparison to bitmaps. Yes and no, less RAM, but it's going to be more expensive to draw. Although internally we can cache vector drawables as bitmaps, so in the end it's just a bitmap. You're writing a 2D game. Yes, you can use Canvas, but you're going to be limited. If you want to do advanced lighting effects and stuff like that, you should still use a game engine. So it depends on your game. White color gamut, we'll still use the hexadecimal notation. Yes, you can still use it, but we will need an extra bit of information explaining what color space you are using. Note that if you look at the color class as of Android.o, we have a new representation for colors using a long, where we can store the color space information. Can we get an entire series on Android graphics complete with art history lessons? Yes, we'd love to do that. And I want to talk more about the eye and the nervous system and how our brain works.
Check development documentation. There's some really good visuals in there about how some of the lighting and vision stuff works.
Any plan to add z-axis transformation, 3 transforms using 2D space? That's been supported for a long, long time, at least since Android 3.0. So look at the set rotation APIs on Vue, or you can use the camera API on Canvas. Do each letter in a glyph cache take up the same amount of space? Yes, if you're lazy, but you're gonna waste your cache. In the cache that we built with Chet, the letters were using the same width, but not necessarily the same height. So it depends. When can we expect part 1? I don't know. Love to hear more about real edge cases. Yes, well, that's a lifetime of working on a 2D renderer, so probably not in a talk.
Excellent. Thanks very much. I hope this was helpful and fun, and we'll see you at a future talk, hopefully part 2.